So this is lecture 44 on embedded maximality by Harvey Friedman. Please.
Thank you. Yeah, so I probably don't have take the full 1 hour. I spent a lot of time agonizing. First of all, I spent a certain amount of time actually even improving on chapter three and I fixed up I aligned everything, and it's an expositional improvement. It's not a substantive. It's not a substantive change, but I did have spent some time having to doctor up stuff, and I want to release chapter three shortly. I'm really kind of um burnt out on chapter three, but I'm hoping to release it well before the next meeting. But but there is something worth going over that I did do. I spent time with that, and then spent a lot of time agonizing about how I want to do chapter five, the finite form. And I finally came to my uh, determination of how I want to do this, and I'm pretty satisfied with it. And so most of today will be on that. Uh, uh, I don't have a, a lot of details on it, uh, uh, clear statements, but I don't have a lot of lemmas and all that kind of stuff yet because I had to spend so much time coming up with this. I had to juggle several ways of doing it, and I've come to think that this is overall the best way. All right. Anyways, so back to chapter three a little bit, and that was small changes in the table of contents. Um, this is where the work starts, if you remember. The the serious stuff starts, and then I have some small but powerful changes here, change here, and uh, I just had to do a lot of polishing in and around here. Nothing new really. Uh, a lot of polishing, a lot of fixing notation, and so forth. Uh, I mean, this will be released soon. Uh, I need to take a fresh look again. And this is wrong here. This is H. Uh, yeah. All right. Well, so let me just talk about that. Yeah. Okay. Yeah. So let's just talk about 3.6. Yeah. Okay. So Um, we're always talking about partial maps from -1, 1 to -1, 1. So it's the identity extension usability. So I think last time we did define, uh, let's see, I don't remember where I put it in the text here, but um, the identity extension of a map, F, you um, you make it the identity above the map and the identity below the map. In other words, above the field of the function and below the field of the function. Right. So you don't fool around with in the middle. All right. So here is now the new statement, slightly different than before. The identity extension of any finite usable F is usable. Period. The identity extension of any finite F is usable. And that is very nice once you accept usability and the chapter 3.5, section 3.5, which is the complete determination of what the finite usable F are. Okay, so this is to me a very good situation. It doesn't even talk about strictly increasing. It's sort of implicit. Don't need to. This is just a statement. The identity extension of any finite usable F is usable. And then the half identity extension is where you take the stuff that's halfway to the end and make that zero, and then halfway to the end below make it zero. So you've now gotten rid of the singularity. There's no singularities anymore, right? It's kind of separated. And this is called the half identity extension. I think we did this before. Now the new statement is just this. The half identity extension of any finite usable F is usable. Okay, and this one is provable in Zermelo, whereas the other one is provable in SRP, well, con SRP, and the reversal is done for the other one we have the reversal from chapter 4. This is equivalent to con SRP over WKL naught, and this one we don't have any reversal because I didn't do weaker reversals in this book. All right. Okay. And then we have the very natural informative calibration. IEU of Kn means the identity extension of any finite usable F with n element field is K usable, and the half identity extension of any finite usable F with n element field is K usable. And then these are just calibration. So they're equivalent when you quantify K and N. When I actually do the work, I actually have a more technical form in which I state what the fields are. The technical form of IEUKN is the identity extension of every strictly increasing F with field this or field that. This one goes to 1 from 0, and this one doesn't go to 1 from 0. The endpoint is missing, is K usable. And then the same thing for this. That's what I actually prove. And then I show that these are equivalent. Okay, so that's enough about chapter 3. Put it to rest. All right, now chapter 5 is what we're after, and I went through a long agonizing process and decided to scrap all my earlier ideas and focus on this new one, this new way of doing it. I'm pretty convinced this is the right way to go. And the official statement is EICD, embedded. I can't remember exactly what these letters mean. All right, we'll come to this. Embedded independent control dominator. Embedded independent control dominator. All right. So the first thing I do is I shift. This is just expositional. I shift from maximal change to maximal independent sets because that's dual, right? And then independent sets are well known to be the same as independent dominators. This is a classic theorem in graph theory due to Claude Burge. Okay, so, and by the way, that stuff is done in graphs, but there's no reason to talk about just graphs. I talk about general relations, which is just as good for this purpose. It's better because it doesn't mean that you have to be a graph theorist, and it's also more general, trivially more general, not importantly more general. All right. And the other thing I do when I get into this really nitty-gritty finite stuff, I focus on the embeddings that drove chapter 4, the reversal. If you remember that this drove chapter 4, the reversal, that that map. And here's the definition from chapter 4. Okay. In other words, it just goes from here to here, here to here, up one by one, undefined at K over K. And then it's the okay, so but why don't I become competent here? This is wrong. There we are. And the usual thing, these are the parameters, right? You see here, like this. This is what we always have been doing. Now, I did the more general theory of usability for an arbitrary map because I didn't want to be accused of being so special. But now that the infinite subject has been completely ironed out in chapter 3, and also in chapter 2 for core math objects, chapter 2, um, one is free to be more specific. That's my philosophy. One is, because we're going to finite world, we can afford to be more specific and not worry about general conceptual matters as much once we laid out the subject at the infinite level, with which we're implicitly pi 0, 1, of course. All right, so the notion of independent set is well known to everybody. S is independent in a relation if and only if it's a subset of the field of the relation, and no two distinct elements of S are related by R. S is a dominator. Here's the definition of dominator. If and only if, and this, by the way, this is standard. This is standard. S is a dominator in a relation or in a graph. They usually do it with graphs. If and only if every point or vertex, if it was graphs, every point there is, given any point, there is a point in S which is either equal to X or related to X. That's the notion of dominator, very important in graph theory. Of course, they usually often talk about finite graphs, but anyways, this is the key notion. Dominators are usually defined for graphs. Yeah, it makes general sense. Okay, now we need to talk about duality. So if R is a relation, the not R is the negation of the relation. And since we're not worried about graphs, we don't have to worry about insisting that in a simple graph, X is not, we have forced irreflexivity. That's irrelevant because we're talking about general theory of relations. Independent dominators are the same as maximal independent sets. Did I misspell something? Just a second. Yeah, independent sets. Independent dominators, yeah. Maximal independent sets, yeah. Yeah. All right. I may want to fix this. I may want to fix this. Maximal independent sets and independent dominators. Yeah, maybe I make that title a little bigger. Oh, I already did. Oh, okay. So I already made the title bigger already here. I just didn't do it in the table of contents. All right. Okay, and now we just have this consolidation. Let R be a relation on X and let S be a subset of X. The following are equivalent. S is a maximal independent set in R. S is an independent dominator in R. And S is a maximal chain in the complement of R. All right. And then we have the embedded maximality chain theorem. Every order invariant relation on every minus 1K has a blah embedded maximal chain. That's exactly what was That's exactly what was reversed, except it was reversed for graphs. But this statement is even stronger because graphs are a special case of relations, and chains are correspond to cliques, are cliques. So this is just the statement being reversed, and then here's the dual of the statement being reversed: the embedded maximal independent set statement. Every order invariant relation on every minus one to the k has a blah embedded maximal independent set. And this was exactly the map that we used when we did the reversal. Yeah, chapter 4. And then finally, this version. Um, every order invariant relation on every minus one k has a blah embedded independent dominator. Okay, and it's trivial that these are all equivalent over RCA naught because of the fact that independent sets and maximal independent sets and independent dominators and Maxwell chains are all the same thing, except you might have to go to minus through the negation of the relation. Doesn't make any difference for this. Okay. And then these are all equivalent over our WKL naught. This because of chapter 4, we know that this and that are okay. This is all just to set the stage for the finite form. All right, so we have this notion of a control dominator, and that's the only thing that we have to worry about. I kind of like this. Uh, yeah. Okay. I mean, I was also looking at height-free forms of this that don't involve the height notion, but you gain so much so quickly from the height notion. I decided to go with this. Okay, so the height. This is totally standard. The height or the naive height, sometimes called the naive height, because the logarithmic height is also considered important. The height is the maximum of the absolute values of the numerator and denominator in the reduced form of the rational. And the height of a vector, a tuple, is the maximum of the heights of its coordinates. And also, it's useful to write capital H brackets n for the set of rationals whose height is this is really not what I wanted. I wanted, let's break this. Just a second. Yeah, the height of n, h of n is the set of rationals whose height is at most n. Okay. So let R be an order invariant relation on minus one to the k. S is a height controlled dominator slash n. So there's another parameter n. In R, uh, if and only if for every x in h of n to the k, in other words, for we did this is just a condition on actually I really this is not really what the way there's a better way to say this. If and only if S is this is what I meant to say. If and only if S is included in h of n. This is what I wanted to say. H1 of the k. And there we are. Uh, if only if S is contained in H of n to the k, and for every x in S, there is a y, Okay, so this is completely screwed up. All right, let's fix this up. Yeah, H of N. This is all what I had a corrected spirit. It's not good enough in math. Okay. All right, let's go over this once more. S is a height-controlled dominator slash n in R if and only if S is contained in H of n to the k. So S just it's just got all these low things. Actually, that's not. Okay. So there are some issues here. Um, let me see what I want to say here. See, because there's two different K's here. Um, this is what I want to say. All right. Uh, yes, this is what I screwed up on. There we are. Here. Uh, okay, there are two K's here. All right. Okay. So be a high control denominator sub n and r. First of all, S is, I got to say that S is just made up of stuff that's not too high up in height. And it's K tuples, but there's also a K here that I use for arithmetic. Maybe I want to figure out, maybe I don't want to use these two Ks, they're confusing. But let's it's correct. And for every X in this space, I can find a Y in S um, such that the height of Y is at most the height of X to the kth power. Yeah, to the kth power. Okay, maybe I got it right now. Okay. Uh, let's see, can I simplify this a little bit? S is a height control denominator. And yeah, I do want to say that S is finite. I mean, that S doesn't have that much in it. Um, and that's fine. Um, and if it's n, it raises it to the kth power. All right, so there's some things I don't quite like about this because a little confusing because I'm using k as the kth power numerically at the same time I'm looking at k tuples. I may want to fool around with this a little bit. And by the way, I didn't do any serious work on the height I need. So I would love for this to be work for just k times height s. In other words, can I just do something like this? Um, uh, K height S. Something like that. I have to look carefully at this. I hadn't had a chance to do it. Maybe this would be much better rather than overkill with the kth power. I have to do some computations to see if I can get away with that. But the idea is that in these dominators, you have every point, there is a point. That for every point in the space, there is a point. Now we only want to do it up to a certain place in the space. So for every point we're worried about, there's somebody that dominates it. To dominate it, you're either equal to it or you're related to it. And I want to make sure that this thing over here that dominates it is got a height that's controlled. It's a controlled blow up of height. It's a controlled blow up of height. Of course, if y is equal to x, we don't have any blow up of height, but we might have it otherwise. So we have a controlled blow up of height. So that's what I mean by a height controlled denominator. The little n is sort of saying where the little n is sort of saying where how far up we're going to go, because a height controlled dominator sub n is supposed to be a finite object, is a finite object, yes. All right. I have to look and see. This might be very nice. There might be a very nice, better control of the heights than kth power. All right, so that you get the idea. And so now we have let's review EID. Every order invariant relation on every minus one with K has a blah embedded independent dominator. And that this is con SRP. This is con SRP as we discussed earlier, and this is the finite form. Every order invariant relation on every minus one to the K has a blah, the same blah embedded independent control dominators sub n greater or equal to 1. In other words, it's got for each n. Yeah. Now, it might be better to say let n be greater than 1 equal to 1. Outside here and put it outside. Let n be greater than 1. Every order invariant relation on every minus one of the K has a blah embedded independent controlled dominator sub n. Yeah, maybe I could do that instead of trying to copy this exactly. So if you're going to make a finite form, the idea of introducing a letter for another numerical parameter is very common. So that's where I'm going with this. Now, one has to prove that EID implies EICD and the converse. And the proof that EID implies EICD is you go to a real infinite, full-blown, embedded independent dominator, and then you have to pick a finite piece of it. And you have to pick the finite piece of it uh, uh, with the inequality for being controlled. And that requires some care, which I've done in different contexts, so it's not new to me. It's some care where you adjust the heights of the numbers because of isomorphisms, because there's all kinds of bijections going on. So the whole thing is order theoretic, right? And so you can do these adjustments. You have to prove that you can do that. And that's a painstaking thing, but not difficult. Conceptually, it's pretty clear, how you go about this. You just have to show that you've got enough room to move things around and keep the heights controlled. And maybe the heights can be controlled much better, something like this, or maybe even better than this sledgehammer of the kth power blow up. So this is a straightforward thing in conceptually at least. And the reversal is interesting. So the reversal, the idea is pretty clear. The reversal, in some ways, is easier. The reversal is simply that you have a finely branching tree. You use Koenigsegg. You have a finely branching tree when you have all these when you have these height controlled things. There's only a finite branching, and you just take an infinite path, and that's going to be your your embedded independent dominator. So actually, the reversal is the easy is even easier. So that's it. That's my current attitude on finite form. Unless something dramatic happens, I think that this is. There's something more dramatic. I didn't quite pin it down properly. I may come up with it, but right now this is a good way. Now, what's the research here? There's some interesting research here, and that is um, detailed discussion of the best possible ways to do these heights so that so that the statement is true. Um, so if you have a sequence, if you have a mapping, let's say you have a mapping. One goes to three, and two goes to five, and three goes to seven, something like that. If that's the height blow up, if that's the height blow up you want, does that work? Now there is a dimension k going on. There is a dimension k going on here. So what I'm saying probably needs to have k in it or something. But you could fix k to be you could in this thing you could fix k to be 2. Remember, I got omega 1 out of stuff like that. Well, I didn't do reversals. All right. Let's let's not go there exactly. But basically, I can ask for detailed information about these heights. Um, and uh, I think if you ask for enough detailed information about these heights, you may be able to avoid even saying that you have an embedding. You might be able to get strength out of. There may be a way to get strength out of this without talking about uh, embeddings just by looking at the numerical pattern, the numerical quantities, or it gets at least some strength. So there's some interesting things, or just behave like a mathematician and want to know how little blow up of heights do I need in order to get this reversed, reversed back to EID over here. Uh, rather than one fixed sledgehammer blow up. All right, now I do intend to put in. So you notice that this is more specialized than the chapter 3 stuff because there I talked about usability. I didn't insist that the function have this shape, that the embeddings have this shape. Although I showed that in chapter 4 that if you have that shape, that's enough to get as enough to get large cardinals. But here I go even further. So I just decided in 5.6 with a non-deterministic algorithm to really roll my sleeves up and be very, very specific, like a computer scientist, so to speak. And not only basically use this function, but use this function unraveled in the algorithm and line up tuples to be processed, to be accepted or rejected. So it's a very uh, computer science friendly kind of algorithm. I might even use the AI to get feedback about much how close is this to computer science algorithms and what way can it be changed to make it more. I would be surprised if the AI would be of use if I push it hard enough uh, to do this, or even have the AI patenting on the back that this is a really cool thing that's very similar to in spirit to computer science algorithms. It might actually praise me, you see, so this might be good. So I definitely want the computer science angle in here. Um, Now, this is very important with another step, which is beyond the scope of the book. This is going to be a non-deterministic algorithm. There's going to be accepting tuples or blocking them. There's a non-determinism in here. There's another weaker non-determinism in here I think I'm going to keep as well. Okay, one that can be eliminated. But basically, this is not deterministic. And so even the question of whether I can go for 10 steps is going to be mind-bogglingly difficult without simply knowing that you can go for any number of steps. The best way to know that you can go for 10 steps is to actually go for arbitrary number of steps and then just say, well, I'll just stop at 10, right? That's the easiest way. And so it feels like that's the only way you can do this, except by a search. So this immediately leads to search questions about whether you can go with a non-deterministic algorithm, say 10 steps. Maybe if you're clever, you can cut the search space down so that you can actually do it and come up with a non-deterministic path of like 10, say. I call that confirmation of large cardinal consistency, or confirmation of large cardinals, if you want to just talk about it that way. Because if I did the search and I failed to find a non-deterministic path of length 10 or so, if I failed to find one, then I've refuted the statement, which means I've refuted large cardinals. That means I've refuted large cardinals. So therefore, if I didn't refute large cardinals, I provided some evidence that large cardinals are all right. That's how the story goes. Now, I've had this idea for quite some time, but there's some issues with the practical implementation of it, uh, and um, and issues about what's realistic in terms of the size of the search space and how much computer science theory could help a lot in cutting down the search space. Uh, and then there's the theoretical problem of how do you justify all this propaganda that I just gave it. Uh, I mean, you can sit somebody at a desk and say, I want you to do 5 steps in this. I want you to do 1 step in this algorithm. Well, that's not a problem, probably. I want you to do 2 steps in this algorithm. And maybe that, they have to think about that for 5 minutes. But I want you to, at some point, you are, as a human being, you have absolutely no chance you're going to get totally lost, totally and completely lost. That's the idea. You get totally and completely lost, which is a very good sign. Now the computer comes to help because it can search a lot, and you can't. You're a carbon-based life. You can't be doing all this search. So, uh, so that's a very interesting interaction between humans, computer searches, and large cardinals. Okay, but not this book. This is just another book. All right. So I will, now that I've fixed my ideas on chapter 5, I will be able to next week give a full-blown version of this chapter 5 with a non-deterministic algorithm, uh, fleshed out, maybe more than one, uh, and the proofs that that's equivalent to con SRP. that there is a path, or arbitrarily long paths. So it's pi 0, 1 explicitly. Oh, I forgot to say, obviously all of this is pi 0 is explicitly pi 0, 1. Explicitly pi 0, 1. Right? Okay, good. All right. I know that you're going to be very pleased that I'm done early. So, Andreas, take it away.